And like you need this for, well, supposedly you need this for future learning, right? Okay, so let's talk about the mean value theorem. Okay, so we've been talking about these type of instances, yeah? We're looking for localized extrema. And what do we notice happens here? So this is a critical point. So what is the nature of this tangent line? Does it have slope 15? Infinity? Zero, right? This is a horizontal tangent line, right, where localized extrema occur, right? This will happen in both of the directions. I just drew a localized maximum. So this is F. This is the tangent line. So we have here that F prime. Let's let it be C. This is 0. Let's call this C down here. Now, we want to be able to find points like this, and we were already discussing that we can bracket them with open sets. Now, if I take this open set and I draw a line through those 2 points, this is a secant, right? This is like I take this line and sort of shift it down a tad. Right, so if this is a localized extrema and I shift this down a tad, we're going to cut the curve in 2 places, and it turns out that this line is going to be parallel to that line. So what's the slope of this line? 0. Okay, so this is an observation called Rolle's theorem, that if you have a curve and you can cut it in such a way where you get a secant which is flat, then it will necessarily be the case that there's going to be a point where the tangent is flat. Okay? That's the geometric sort of explanation of what Rolle's theorem is. So I'm going to write Rolle's theorem, which is going to be the algebraic codification of this geometric picture. Okay. So here's Rolle's theorem. Rolle's. Okay, so here's the stuff that people usually screw up, right? So I always write on theorems, especially named theorems, that the theorem only holds true provided something, right? Provided F, in this case, is continuous over AB and f of x is differentiable over what we call the interior of this. It's basically the closed interval, but you remove the boundaries. Then if f of a is equal to f of b, this implies there is a c in this interval such that the derivative is flat. So these are your secant points. This is the point in between, and this is the codification that it's equal to 0. Right, so again, if you can find a secant that's horizontal, all you have to do is shift this secant up or down to find a local extrema. This always has to happen. Okay, proof. Omitted. I know how much you hate them. I'm smiling. Half smiling. Okay, so it's a very simple statement, right? So the reason most people lose marks on these questions is they don't explicitly, practice is one of them, but you need to explicitly state that these provisions have been satisfied when using the theorem. It's like a toll, it's like a payment, right? So you can't cross the theorem bridge before you pay the theorem toll.
You have to prove it, you have to prove that the function is continuous.
It's usually the case that the function is like continuous because it's a polynomial, right? Or you just basically have to identify the points of discontinuities and remove them, right? I won't ask you to prove anything's continuous. You don't have the power to do that, right? We haven't given you the mechanisms, but you can say like polynomials are continuous and differentiable, right? But I don't even think we're looking for an explanation. We're literally just looking for the statement f of x is continuous and differentiable, therefore I'm allowed to use this. right? But you have to mention that before using the theorem, because maybe you'll give you something where it won't work, right? And you'll have to say that as well. Okay, so I'm going to give you here's an example. I want you to think about this for a bit. Okay, this is a combination of IVT and Rolle's theorem. Show this function has exactly one solution. Give that a go. Okay? You can't factor this. So it's going to be hopeless to find them, I think. But in any case, don't try to factor it or anything, right? You have to I want you to show that this has exactly one solution, which is a different question than asking you to find the solution, which may be impossible or at least very difficult. Right? So first use intermediate value theorem to show this has a solution, and then we'll try to use Rolle's theorem to show that it's unique. I'll make one lap.
And you can't calculate an entropy?
Huh?
No specific entropy?
No. That's the other way we could trick you. That's how we tricked you on the practice midterm. I gave you an interval where the endpoints weren't the ones that you wanted. You had to pick something inside. You get to choose the interval. This is more flexible than me giving you an interval. How was your shirt? Very much.
Yeah, because I need to check, I need to check what's positive. And it's just like what's positive. Yeah, so it's not
Have you shown that? So here's a question. Have you shown that the function has a solution? Okay, so it's the line. Okay, but you have to say you have to use the codification a lot more rigorous than that. That tells you that it's at least it tells you nothing about if it does it exactly. You may hit the axis 100 times over that error. Right, so the intermediate value theorem says yes, we do it doesn't say anything about the number of lines. So your answer to your question is you need Rolle's theorem to get the same. Show it has exactly one solution. So the solution value literally underlying the board. Right? You just don't like proofs. There's some weird prejudice. But you get one solution from IVT. Now you have to show that solution in the solution. Because it will be a problem if something has multiple solutions that may have sort of weird consequences. Like, oh, our braking system is going to fail under these conditions. Okay, well, here. Yeah, what about all the other times? You found one solution. What if there's 100 cases for the braking? Please demonstrate that this is the only time it's going to fail. Then you don't have to do this. These are like snippets, again, like intellectual masturbation. This is happening in the real world. There is a real world consequence for this equation. That is damn well. Solutions we found is the only thing. These are the two. This is, we're not playing this game, but this is why it won't work. For these reasons, so you shouldn't be with it without you need them. You need them. Math doesn't fall out of the sky. It holds developed by us. And then we get to
What if it be like this? Like
there's a huge long history of we have to appreciate
what are you saying? The second.
It's only this one.
infinity, negative.
Oh, just understand. So can I say it's a square root of 3 over 3?
Got to think more abstract.
Right now, this one, right now, this one.
Don't even treat them.
Yeah, because I took the derivative.
You're gonna want to
That's what almost theorem says, right?
I don't know why I think that was a better example. It doesn't matter to me, like, this is an account. You're not coming here and adding up numbers from both. That's how you guys want this to work. You're gonna go out to the world and you're gonna say, we have a problem, we need to solve this problem. You will be surprised how the simplest of problems require crazy complicated
The point is,
if you look at this closely at all, I'll show you when we start doing integrals, like how much they appear naturally everywhere. And they're not easy. Integrals are hard.
Don't know if I can.
That's okay, I'll do it on the thing. Okay.
Well, I don't think, what if you use one?
say, okay, we have one solution.
At least.
We have at least one, and now we want to use roles to say that we want to use roles to prove that this is
And then
The
you
only-
take it crosses out.
No.
If you just do it
What does the extreme have to do?
well, if it's
It's not an extreme if it's crossing through P. It's not necessary. Roots and extreme aren't the same thing.
yeah, they're not the same thing.
So why did you bring extreme into this?
Here's the thing.
Well, what I was thinking.
Because that's a extreme.
The function is odd. How are we going to get two x values that is the same line?
You will if there are two solutions.
But there's exactly one solution.
No, you found there's at least one
You
solution.
asked us to prove that
If there are two, then there is a consequence, which is impossible. It's okay, right? We're never going to ask you to do these. I just want to demonstrate that, like, if you think, you can get these results.
Yes.
You're very close, right? You sort of assume that there is two solutions and then show that something's stupid. No, I'm telling you how to solve it, right? No. Oh, okay, sorry. Here you go. Like,
I'm telling you what I was trying to say to you.
you assume that there's two solutions,
Okay.
and then you get a consequence from that. Okay, any ideas out there? So we're going to do this, then we're going to do mean value theorem, and then I'll just give you a bunch of problems. Okay, so did you manage to use intermediate value theorem to demonstrate that a solution exists?
Yes.
Okay, walk me through the argument. Pay the toll first, right? Yeah,
So we said it's continuous because it's a polynomial.
great. Okay, so f is the polynomial, which implies f is everywhere continuous and differentiable. Big check mark. Marks already, right? Just for saying that. That's the way I get you guys to pay attention. Marks. Marks for doing this. Okay, what next?
We use the x values -2 and 2 to prove.
Okay, so f of minus 2 is what?
-13.
Minus 13, which is less than 0, and f of 2 is what?
15.
Is what?
15.
15, which is greater than 0. Okay, so by IVT, another check mark, right? We have that there is a c in -2 such that f of c is 0. Okay, so we have proved, right? Therefore, there is at least one solution. Notice that the intermediate value theorem tells you nothing about the number of solutions, right? There could be 100 solutions in between -2 and 2, right? Intermediate value theorem says, well, there's at least one, at least. Okay, so this is half the question. We've shown that there is a solution. Next, we have to show that that solution is the only solution, is a unique solution. So I'm going to walk you through that argument. Okay? So suppose I'm going to write something funny towards a contradiction. Right? So this is basically a warning to people reading the proof that I'm going to introduce a statement which is going to lead to something absurd. Right? And thereby the statement I made has to be wrong. Okay, so suppose towards a contradiction there are two solutions. There is x1, x0 and x1 such that x0 is not equal to x1 and f of x0 is equal to f of x1. Okay, and I guess I should say that these two are in the interval. Okay, so I'm saying, okay, intermediate value theorem found me one of the solutions in this interval. It didn't tell me how many it found. There may be two. Okay, so let's assume that there is two solutions in the interval. The first one's x0, the second one is x1. What does Rolle's theorem tell me now?
But there's a value C in between, which the derivatives are like equals.
Right. So by mean value theorem, Rolle's theorem. Okay. There is a number. I can't use C. I've used it already. So let me use D. N minus 2 to 2, such that f prime of D is equal to 0. Agree? That's what Rolle's theorem guarantees that this is the case. Does anyone agree?
Yeah.
Yeah, this is just a statement of Rolle's. Okay, I got you a little bit further. Think about what this means. Okay, what is the derivative of D?
0.
Right, but like what is it geometrically?
Horizontal line.
Well, what's f in this case? Where did I write f? Did it go? Oh, here. Okay, namely, what is f prime?
3x squared plus 2.
What is this saying? It's saying I found a D where the derivative is 0. Yeah? Stare at this. Can this ever be 0? Why? Yeah, it's this parabola. Everyone see that? This is 0 nowhere. So what does this mean?
It's wrong.
This is wrong, right? This can't be true. If this was true, then Rolle's theorem is false. Rolle's theorem isn't false. I proved it, right? So this is contradiction. That's how you write contradiction, right? So this can't happen, right? So therefore, there is unique solution. I'll never ask you to do something like this. It's just hard to find actual applications of Rolle's theorem. I show you because you have to see it. Right, just so you know how the underpinnings work a bit.
Sorry, did you just prove that there's exactly one solution?
Yeah,
using that?
because I proved that a solution has to exist by intermediate value theorem. And then I said if there's two solutions, Rolle's theorem is false, which is stupid. Right? So I proved there exists a solution and there can't be two. So I proved that there's exactly one, right? Using maths. So just let that, so this is what we don't do in this course, is these types of arguments, which is sad because they're fun. Helps you think. Makes you really good at arguing. How much time do we got left?
15 minutes.
Oh, okay. Okay, because like think about this. I can't give you a question about Rolle's theorem that says, here's a curve with two, like with a secant that's flat. Show me that there's a flat tangent. That's like way too easy. That is just a trivial application of it. I'm gonna have to hide like Rolle's theorem and mean value theorem questions behind word problems, where the answer to the word problem will be apply the mean value theorem and you'll get it. Right? But I can't just ask you a question, apply Rolle's theorem here. Right? It's too easy. You just have to write f is continuous, f is differentiable, apply Rolle's theorem. Right? So these will always be hidden behind word problems. Okay, so Rolle's theorem isn't that special. It's just easier to prove Rolle's theorem. The actual theorem we need is the theorem called mean value theorem. Okay, and mean value theorem is the codification of this observation. It's very similar to Rolle's theorem. If you have a curve like this, and you find 2 points on the curve, and you run a secant through here, then in between, I'm going to label these things here, you have A, you have B, in between these 2 points. So we're going to play the same game. So with rolls, this line was parallel, or horizontal. Now it's just curved a bit, but we can still move it up and down. So mean value theorem says if you could find 2 points like this, there's going to be a tangent here that is parallel to that secant at some point, right? C. We may not be able to find it, but mean value theorem provides it. That is the world's straightest line, isn't it? Okay. Okay, so how can I then codify this geometric observation into an algebraic statement? That's not too bad. So what we have here, okay? So basically I'm saying that the slope of this line is going to be equal to the slope of this line. The slope of this line is what? It's going to be change of y over change in x. So change in y in this case is f of b minus f of a over, that's the change in y. The change of x is going to be b minus a. So that means, so let's finish this, provided, okay, f is continuous on AB and f is differentiable on AB. If you guys want easy marks, these are easy marks. You just got to write it, and we'll give you marks. Then there is a C in AB such that the derivative, or the slope of the tangent line, is equal to the slope of the secant. The reason this is called the mean value theorem is because in some sense this is the average value of the function over this domain. We'll get to that later once we start integrating, but these are like averages. That's where mean comes from. Okay, so does this codify that? Right? Provided that f is continuous and differentiable, you can connect any 2 points on the function and find a point where the tangent has that slope. That's what mean value theorem says. Okay, I'm going to show you how to prove it, but I'm only going to give you a sketch. So the whole reason that we introduced Rolle's theorem is because it's easier to work with these flat ones than it is to work with these curved ones. So what we do is so if this function coming out of here is f, and then this secant line here is L, then if I draw the function f, so let h be the function minus the line, right? So h essentially is going to be this distance. How can I draw h of x now? Well, the difference between the line and the dot is 0 here. The difference between the line and the dot is 0. So actually it ends up looking like this. And actually the point C now is just the point which goes flat. Right? So I just introduced this function, and now I can use Rolle's theorem on this and lift that result to this guy, which I won't do. But basically that's what Rolle's theorem is for. We use it to get something stronger. Okay, so here's an example. I'm just going to draw you a picture, and then I'll give you some exercises. So if I tell you this is the displacement, right? So here's a time t, here's displacement. I have a function that does this. Okay? First of all, if I connect this line, or this dot with this dot, from time 0 to time 1, what is it? What is the slope of this line? Well, rattle off some of those words I taught you when we did physics. We have displacement, We have velocity, average velocity, instantaneous velocity, and instantaneous and average acceleration. So you got to remember, if this is a graph of the displacement, then the slope of this line is the average velocity over that interval. Right? So slope of this line is equal to the average velocity over T0 through T1. Okay, but that means mean value theorem says that we're guaranteed to find another point here, C, where the lines are tangent. Now this has a very special meaning for displacement. Right, so this means that if you know that the average velocity between some time interval is like 10 kilometers an hour, mean value theorem is the tool that you need to make the statement the person was definitely driving 10 kilometers an hour at some point in their journey. Right? So I'm going to give you a question, and the answer is going to require mean value theorem. So that's the teaching I got for today. The rest I'm going to write are going to be exercises for you. So I hope you stick around to do some work with me. Otherwise, you are released. 10 minutes we have. Oops.